Let's cover some basic terminology and nomenclature. We'll use this animation for demonstration purposes. The mini mill is really a very simple machine made up of a base, column, and head. The mill head attaches to the column and contains, among other things, the gearbox, the motor, and the spindle. The spindle is the rotating shaft that your milling tools will be attached to. Attached to the base is the mill table, also known as a compound table. Now the upper portion of this table has slots cut into it which will accept T-shaped anchoring nuts. Now this is known as the bed, where we'll mount our work or various vices or fixtures if we need to hold our work in some special manner. This compound table is able to move in two different directions or axes. The amount of movement is controlled by the hand wheels. Now each hand wheel has a movable collar which rotates with the hand wheel, but it can be reset to any starting position we might require. The collars are inscribed with tick marks. Now, each of these tick marks is the equivalent of a thousandth of an inch table travel on its corresponding axis. You may have noticed in the picture, or on your own mill if you have one like this, that the tick marks add up to just a touch over 62. That's because each turn of the hand wheel moves the table on its corresponding axis 62 1/2 thousandths of an inch, or 0.0625. Now while this may seem a little unwieldy at first, you'll quickly find that for most common inch measurements it works out very nicely. We'll do more on that later. The last thing in this picture that I'd like you to notice is the witness mark, and that's the mark you align your tick marks against when you make your measurements. Now let's name and demonstrate the basic mill axes and how we move along them. As we mentioned, the main table of our mill can move in two different directions on two different axes. The first is the x-axis, which is left to right movement as we face the machine. This is controlled obviously by the right side hand wheel. The other axis that our table moves on is the y-axis. Now this is front to back movement as we face the machine. So, much like the Etch-a-Sketch toys you may remember from childhood, by using these two axes we can position any point on our workpiece under the mill spindle. But we still need a third dimension, that of depth. That third axis, the z-axis, comes from movement of the mill head on the column. We're able to raise and lower the spindle in relation to the mill table in much the manner of a drill press. As the animation shows, that can be done with a hand wheel that's on the side of the mill head. But that only gives us coarse control of movement on the z-axis. We're looking for precision movements. We can measure in thousandths of an inch. So besides a coarse feed hand wheel, we also have a micro feed or fine feed dial on the front of our mill head. Now we can use the hand wheel when we're using the mill as a drill press and for other large movements of the spindle. But when we want precision, we engage the micro feed dial. You can see that between the mill head and the hand wheel there are two castellated or square-toothed rings. Now these act as a simple clutch to engage or disengage the micro feed dial. When apart, as in the picture, the hand wheel will move the spindle head as desired. But when the hand wheel is moved inboard towards the mill head, the two rings can lock together. When this happens, spindle movement is now handled by the microfeed dial, and with some care can be controlled very precisely. A look at the side of our microfeed dial shows us that it too has a movable collar, graduated in tick marks that also represent a thousandth of an inch. You probably noticed, though, that this dial ends precisely at 60 thousandths. Now this is important to keep in mind when we get to the calculating portion of our presentations, and we're trying to figure out how many turns of any particular hand wheel or dial we need to locate our work in relation to the spindle. Since we've mentioned calculations and measurements, this might be a good time to bring up a factor that we need to be aware of when we're using our mini mills, lathes, or any precision mechanical equipment. It's called backlash. Mechanical parts, such as gears and screws, do not mesh with each other perfectly. They need to have a small amount of clearance or play between them. If you would, take a look at the drawing on your screen. Let's say the screw represents a cross-section of the screw that runs through the x-axis of your mill, and the red portion will represent a cross-section of the nut that attaches it to the actual mill table. Now in this drawing, they're meshed perfectly. There's no space between them whatsoever. So, if the screw turns and exerts pressure on the nut, it's going to follow without any hesitation or lagging. Now that'd be real nice, but in the real world it doesn't work like an animation. There has to be some space between the parts where friction will make it impossible for them to move at all. Now, not only is there some play that's actually designed into the parts, but wear and tear are also going to take their toll, adding additional clearance between the parts as time goes on. Now that presents a problem because that's what causes serious backlash. As the screw begins to travel, it now has to close that gap before it actually contacts the nut and begins to move the table. And if you back the screw off, it again has to cover that distance in reverse before causing any actual movement of the mill table. Now, all of this play in the system, well, it can wreak havoc on your accuracy. Now you can make some adjustments on your lathes and mills to remove some of the backlash. We'll cover those in later installments, but you can't get rid of it altogether. If you hold tolerances too tight, the friction will make it impossible to turn the hand wheels. So you learn to deal with it by making all of your cuts in one direction. Now I've adjusted my mill with a little extra play to provide an example. Suppose I'm trying to locate the spindle on the 15 thousandths mark, and I just dial right past it. Now if I turn the hand wheel back to 15 thousandths, it won't move the table at all. The wheel merely flops around. Instead, I need to back the hand wheel off at least a whole turn to get past the backlash. Then I can come forward again until I reach my desired measurement. Now if I do it that way, it'll remove the backlash from the equation and it'll keep the placement very accurate. Going back to our animation, we have one more movement available on our mini mills. To cut angles in our workpiece, we can swing the head of the mill to either side around 45 degrees each way. Now this is a very useful feature, but most of the time we're going to try to avoid using it. The reason is, whenever we move the mill head out of alignment, we have to reset it back, and we have to do that very precisely. This process is called tramming the mill, and while it's not terribly hard, it is a little time consuming. So whenever possible, we'll try to avoid this. To do this, there are different types of vices, tables, and fixtures that will allow us to select angles for our workpiece while still leaving our mills in normal alignment. If you're new to the hobby, you've just covered a good bit of material, but as I'm sure you found, it really wasn't very complicated or intimidating. We'll be using these terms throughout this as well as the other presentations in this series. So if you feel you missed something, a quick review wouldn't be a bad idea. That's a nice thing about DVDs and VHS tapes. They're really very patient. When you're ready, we'll go ahead and take a look at some of the tools and accessories that we'll use when clamping our work.